Everybody, so here we have chapter 5.3 of the Clausius-Clapeyron relation. And here we're talking about the relationship that exists between the pressure and the temperature and the entropy and the volume. So the idea behind all this is that in a phase diagram, the Gibbs free energies must be equals two um, for two states. So, for example, the Gibbs free energy for the liquid has to be equal to the Gibbs free energy of the solid, or the same thing, Gibbs free energy of the liquid has to be equal to the Gibbs free energy of the gas. So, this means one other way to think about this is that the chemical potential has to be the same for two different states. So again, potential liquid is equals to chemical potential of solid, and chemical potential of liquid is equals to chemical potential of gas. They're the same particles in the end. Um, so the Gibbs free energy per molecule must be equal. That is something that we have actually seen in chapter, I believe, 5.2, towards the end, where defining Gibbs free energy is equals to n divided by, n times u. And if we're saying that G is the same, well, we're talking about one single particle, then we divide this by G, the N, and we get that mu. Of course, these are different particles, I'm going to have different states, so state 1, state 2. I'll say that mu 1 is equals to mu 2. So if we write down the whole formula for the Gibbs free energy, we have that it's equals to negative T times ds plus V times P. One second, I don't want to say anything wrong there. It gets confused. So S times dt. That's how I was confused. Okay, S times dt plus V times dP plus mu times dN. So we're saying that these Gibbs free energy for two states are the same. So for example, the entropy of a liquid will also be times the dt again, this whole thing, plus volume of the liquid times dp plus mu of the liquid times dn has to be equals to, again, the Gibbs free energy of, let's say, a gas. We can also do a solid, it doesn't matter. So it's to negative entropy of a gas times dt plus the volume of a gas times dp plus chemical potential of a gas times dN. Now we said that the two chemical potentials are the same, and the number of particles are also the same. Because of course we don't just increase the number of particles going from a solid to a liquid. So we can cancel out these terms on both sides. And we end up having negative S, or entropy of the liquid, times dt, plus volume of the liquid times dP, is equals to negative entropy of the gas times dt, plus volume of the gas times dP. Okay? And we can write a little bit better. We can say, for example, that let's move the pressures on the left. So we would have volume of the liquid times dP minus volume of the gas times dP is equals to the entropy of the liquid times dt minus entropy of the gas times dt. So now we can collect dP from the first part. So we have dP times volume of the liquid minus volume of the gas equals to dt times entropy of the liquid minus entropy of the gas. So we can say that dP divided by dt is then equals to the entropy of the liquid minus entropy of the gas divided by volume of the liquid minus volume of the gas. Or, even better, dP divided by dt is equals to delta in entropy divided by delta in volume. This is pretty much it. We can also rewrite delta in entropy divided by delta in volume as delta in heat divided by temperature times the change in volume. So we can say that dP divided by dt is equals to latent heat divided by temperature times delta V. Okay, this is pretty much it. There's not much to add to it. As I said, this part of the chapter is fairly small, fairly short, but it's all you need to know. So I hope this was helpful, and let me know if you have any questions or comments.